All right, so we're looking at parametric equations in the next section. And what parametric equations are, they're just equations that are two-dimensional equations. So you have an x and you have a y, but then they throw a third variable in there. And a lot of times you want to look at not only a function's position, but you might want to look at a certain position at a certain time, and that would be the third variable then. So that third variable is called a parameter. And a parameter, it could be an angle, a lot of times it's time. They're the two big functions that we'll look at, but it could be any third variable that you throw in there. So we're going to go through and look at the curve that we're going to create is called the plane curve, and sometimes they'll call that plane curve C. And it's what is the x position at that particular parameter and what's the y position at that particular parameter. Okay. So we'll go through and we'll start graphing some of these so you can see what happens with these parametric equations. You need to plot these problems in a particular order because you want to show the position at a particular time, whatever that parameter happens to be. So for this first one, you have a curve that's given by this parametric equation. It's a set of equations that gives you an x value and a y value. X is equal to t squared and y is equal to t minus 1. And they want to know what is that, the values for that from t is -3 to +3. So you're going to plug in the values for x into that x equation there. So if I plug in -3 and I square it, I get 9. If I plug in -2 and I square it, I get 4. If I plug in -1 and square it, I get 1. 0 will give me 0. 1 will give me 1. 2 squared would be 4, and 3 squared is 9. So that's the first piece of it. That's the position that x is in at those particular times. Then we're going to find the position that y is in at those particular time values. So if I plug in -3, -3 minus 1 would give me -4. -2 is going to give me -3. -1 will give me -2. 0 gives me -1. 1 will give me 0. And 1 and 2. And then what we do, graph the parametric equation. And I keep saying t is time. Typically t is time, but you have some negative values here, which usually for time you talk about time as being positive values. But they gave us the definition that t could be from -3 to +3. So don't get hung up on the value being negative there. So we're going to plot these values as ordered pairs. We're going to plot x values and y values on your xy plane there. So when t is -3, x is 9, and y is -4. So let's extend this a little bit here. So 9, -4. So that's my starting point. And then when x is 4, y is -3. It's going to be right about there. When x is 1, y is -2. When x is 0, y is -1. And then we have 1, 0, 4, 1, and 9, 2. So the graph started down here, and then through these points, and ended up back here. So another thing that we're going to do is we're going to show the orientation for the graph as well, and that's just the direction that we headed as we started. So I just put some little arrows on there. This is where t was -3, and this was where t was +3. Just so you can see the direction that you're headed. So that's what you're doing to graph these parametric equations. We'll go through graphing them in the calculator as well, but just to give you an idea how to graph them by hand, it's not too bad. This one's in terms of our parameter is an angle this time instead of t, which we usually think of in terms of time. But we can go through and do the same thing for this. So x is the cosine of theta. If you think of your unit circle here, we could look at a couple other points as well. If you think of your unit circle, my x coordinate is my cosine coordinate. My y coordinate is my sine coordinate. So we can fill a few of these values in right off the bat. My x parameter is cosine of theta, which is my x coordinate. So when the angle is 0, my x coordinate is 1. We'll skip up to pi over 2, 90 degrees. My x coordinate is 0. At pi, my x coordinate is negative 1. At 3 pi over 2, or 270 degrees, my x coordinate is 0. And back at 2 pi, my x coordinate is 1. And then we also have some other angles here to fill in. We can go through and find, there are multiples of 45. So if I look at a 45-degree angle in the first quadrant, that's 45, or pi over 4. My cosine would be adjacent over hypotenuse, which is 1 over root 2. And since I'm graphing this in parametric form, 1 over root 2, you might want to rewrite that as a decimal is fine. 1 decimal place is okay because you're not going to be able to graph to the 3rd decimal place accurately. 3 pi over 4, that puts us back here in the second quadrant. Cosine would be negative 1 over root 2, which would be negative 0.7. 5 pi over 4, that's in my third quadrant. Same value, negative 0.7. And then 7 pi over 4 puts me in this fourth quadrant here, which is going to be positive 1 over root 2, which is positive 0.7. So that was all of my cosine values there. We'll go through and do our y values, which is 3 times sine of theta. So each of our values will have to multiply by 3, but the process is the same there. So if I go through, let's look at the quadrantal angles first. So my sine coordinate is my y coordinate. So my y coordinate at 0 is 0, and if I multiply it by 3, because I have 3 out in front there, it would still give me 0. At pi over 2, my sine coordinate is 1, which is the y coordinate. If I multiply 1 by 3, I get 3. Oops, I put that in the wrong spot. At pi, my y coordinate is 0, times 3 would give me 0. At 3 pi over 2, I have negative 1, times 3 would give me negative 3. And at 2 pi, I have 0, times 3 would give me 0. And then we need to do the same thing with these values in between here. So 45-degree angle, my sine is 1 over root 2, which we said was about 0.7. But my value for y is 3 times that 0.7. So that's going to give me about 2.1. And 3 pi over 4, the sine is still 1 over root 2, which still gives me positive 2.1. In the third quadrant, sine's negative 1 over root 2, which is about negative 0.7 times 3 would give me negative 2.1. And then finally, 7 pi over 4, the sine is still negative. It's negative 1 over root 2 again. Times that 3 gives me about negative, let's try this again, negative 2.1. Okay, and then the last thing would be to go through and plot all of these points on my XY plane here. So I didn't put a grid for this one in my notes here, or in your notes. So we'll go through and just graph these things. So let's see, we'll have X values look like they go from negative 0.7, negative 1 to positive 1. Let's make that a little bit smaller because Y's have to go up to 3. There we go. All right, so we can plot these points. So at X is 1, Y is 0. That's my starting point. When X is 0.7, Y is 2.1. When X is 0, Y is 3. So I'm going in this direction here. When X is negative 0.7, Y is positive 2.1. When X is negative 1, Y is 0. X is negative 0.7, Y is negative 2.1. X is 0, Y is negative 3, so it's continuing in this direction. This looks like a shape that we just learned about. And then finally, X is positive 0.7, Y is negative 2.1. And then we finish back right where we started there. So if we throw some directional arrows in here, this is where we started. And then we went around in this direction, counterclockwise there. So if you look at that, the equation for that, then that shape looks like an ellipse. I can go through and I can eliminate the parameter and rewrite this in rectangular form. If you look at the graph that we came up with, the graph that we came up with is not a function, but we can graph things in our calculator. They're not functions if we put it in a different form, which was this parametric form. If you want to revert back to rectangular form, you have, let's see, x equals cosine theta. We have y equals 3 sine theta. These are a pair of parametric equations here. So you know one equation that involves x's and y's and your trig functions. Think about this one. Sine squared plus cosine squared equals 1. That was one of our identities. If I take out cosine squared and replace it with what it's equal to in terms of x, I would have, instead of cosine, I would have x squared. And sine squared, well, I don't have sine, but I could solve this equation here for sine. I could make that y divided by 3, and then I would have y over 3 squared. And if I squared the top and bottom, I'd have y squared over 9. I'm going to put the x squared first, and I'm going to put it over 1, because that's usually how we see the equation of an ellipse. And it's equal to 1. If you think about what we just did, the center for that would be 0, 0. My a value would be 1. My b value would be 3. So in rectangular form, my center is at 0, 0. My a value says I would go left and right 1 unit. My b value says I would go up and down 3 units, and those were the vertices for your ellipse. So the graph looks the same in rectangular form as it does in polar form. It just gives you some direction, and it accounts for that third variable there. All right, let's try one more. Same idea. Now this one has logs in it. You can put these things in your calculator. You don't have to worry about not being able to graph them. So we'll look at this one and then we'll put it in the calculator. So if we look at, let's see what these values are. All right, so let's plug some numbers in here. So my x, I'm going to write this down here. So x is ln of 2t. If I put some values in there, well, if I plug in -1, I would have ln of 2 times -1, which is the natural log of -2. If you remember anything about your logs, this log value, the value you take the log of, has to be a positive value. So it's undefined there at -1. If I plug in 0, I'm going to have 2 times 0. The ln of 0 is also undefined. Remember, the values that you take for a log have to be positive values. Right, so then you can plug the rest of these in your calculator. The natural log of 2 times 1/2, we don't really need a calculator for this one. Ln of 1 is 0. If I plug in 1, I'll have natural log of 2, and that we would like a decimal for. So if you put that in your calculator, you'll get 0.7. Ln of 2 times 3/2 is our next value, would give us natural log of 3, which is about 1.1. If I plug in 2, I'll have ln of 4, and ln of 4 is about 1.4, 1.6, and about 1.8. So just plug in those values in, those t values in up here, and multiplying by 2 and taking the log of that. And then the second parametric equation was y equals 2t squared. So we're going to take those t values and square them. Well, -1 I can plug in. -1 squared is 1 times 2 would be 2. If I plug in 0, I'll have 0 squared, which is 0 times 2 is 0. If I plug in 1/2, I'll have 1/2 squared, that's 1/4, times 2 gives me 1/2, or 0.5, and use decimals is fine. If I plug in 1, I'm going to have 2, and so you can keep plugging these values into this equation then. 8, 12.5, and 18. And then if we go through and we graph these, the first 2 values for t, these 2 values when x was undefined, we can't graph those. That we can start at 1/2 them. So x is 0, y is 0.5. I changed the increments on here. I'm going to go up by 2's for this instead. These numbers get pretty big pretty quick. I'm going to go all the way up to 18. All right, and then my x values only go from 1 to 2, so I'm going to change this. I'm going to make this 1 and make that 2. All right, so if we plot these points, then we have 0, 1/2, so it's about there. We have x is 0.7, y is 2. So 0.7 will be right about here, and y is 2. X is 1.1, y is 4.5. X is 1.4, y is 8. X is 1.6, y is 12.5. X is 1.8, y is 18. So the graph's kind of looking like this here. And it's going in this direction. Okay. And they only gave us those values there, so we'll stop when it gets to 3. I don't know if they want it to continue on or not. So that's the first part, and then they want us to write this by eliminating the parameter. We want to get rid of the t's in the equations there. So I have x equals ln of 2t. I have y equals 2t squared. So if I take this first equation here, if I rewrite this as x equals ln is log base e of 2t. I want to get t by itself. So if I rewrite this in exponential form, I'll have e to the x equals 2t. So t is 1/2 e to the x. The reason why I want to get the t by itself is because then I can take my equation for y and I can take out the t and I can replace it with what t is equal to in terms of x, which is 1/2 e to the x. And if I multiply those two things together there, oh wait, I forgot my square. It was 1/2, it was 2 times 1/2 e to the x squared, right, the t is squared. So if I simplify this, I've got 2 out in front, 1/4 e to the x, and it's squared, that'll make that 2x. It'll give me 1/2 e to the 2x. So that's my equation in rectangular form then. And some of them are easier to rewrite than others. The last thing then is putting these in your calculator. You can follow the steps right on here. It's not too bad. You can graph in parametric form. If you go into your mode and you change your mode to parametric form, which is, oh, back up here, my bad. Where you see function, I'm going to arrow over to, it's being difficult on me here. Here we go. Arrow over to parametric form. This is on the colored version. This on your notes there is the regular 84 version. So PAR, or it'll be spelled out parametric. Hit enter to lock it in. You want to be in radian form. For some of them it matters. In this case it will because we're graphing trig functions. And then if you hit your y equals, you're going to see that your y equals now looks like something in terms of x1 and y1. So clear out whatever equations you have in there. We're going to put our new equations in, which were secant. So secant is 1 divided by cosine. And when you hit your x button now, what's going to happen is it comes up as t because you're in the next form, which is parametric form. And then we had tangent. Well, tangent we have a button for. It's tangent of x, and it'll pop up as a t. And then let's change your window. For number 3, I give you what the window should be. Your t is the angle measures your parameters. You can type that in as 2 pi for your maximum, and it'll convert it to a decimal. The t step, I have it as 0.1. You can leave it that way, or you can make it, pi divided by something there. And then my x values, we went from -4 to 4, so make that match up. The scale of 1 is good, and y's can also go -4 to 4 at the scale of 1. And then if you hit graph, you're going to get some kind of function here. The diagonal lines are actually the asymptotes. It's really this piece that you're looking at here. Some of your calculators may give you those asymptotes, some of them may not. And This is like two kind of U-shaped graphs facing away from each other. We didn't do any of the graphs for these, but you know what the name of that graph is when we slice that with Play-Doh. That's a hyperbola. Hyperbolas in two different branches there. So you can graph with the in the parametric form. The only thing is you'd want to make sure when you're finished graphing in parametric form, so you don't curse at me when you go back to your science class, hit your mode, go back and highlight function, and that will put you back into your rectangular form. You hit y equals, you'll see it's the rectangular form again. Hello.